All right, we're going to be talking about our rolling example now. So what we're first going to do is look at an object just like we have in the past that slides down a ramp, and then we're going to look at an object that rolls down a ramp instead. So here's our ramp, pretty standard setup. Okay, angle theta. We've got this object up here that, depending, is either going to slide or roll down the ramp. I'm going to say it's a sphere, either sliding or rolling down ramp. Okay, we're going to look at sliding first. The two things I want to look at are the acceleration, for the sliding part, for the acceleration if there is no friction acting, if there is no friction acting on our object. And also, I also want to look at the minimum force of friction that it would take to hold the sphere in place. So what we would do is we would draw a free body diagram. Our axes would be tilted because we're on a ramp. And we would label our object, object M for mass. We have a normal force pointing perpendicular from the ramp surface. We have force of gravity pointing straight down. And we have, well, if we did have friction, it would be pointing up this way. So I'm going to include it, but at first we're going to be pretending that there is no friction. So what we need to do is we need to break FG into components since that's not lined up with either Y or X. There we go. And there. Okay. And what we need to do is figure out where this theta comes into play. If you were to extend this line, you see that we kind of have the shape of the ramp right here. We have a theta down here, which means because angles in a triangle have to add up to 180 degrees, this angle up here must be 90 minus theta, not very useful to us. However, this component and this component are at right angles to each other, so if this is 90 minus theta, this component must be theta. So this component becomes Fg cosine theta, this component is Fg sine of theta, okay? And we're doing the case if no friction and it's sliding, and so we write our net force equations. In the x direction, it is simply Fg sine theta equals max. Fg is really just mg sine theta equals max. So we cancel out the m's. We're left with this, ax equals g sine theta. The acceleration of this object down a ramp, if there's no friction, is dependent only on the acceleration due to gravity and the angle of the ramp. Interesting. Now, if there is friction, we want the minimum mu to hold the object in place. Okay? So now our F net x is going to change. F net x equals Fg sine theta minus the force of friction equals max. And in the x direction, if friction is holding this object in place, we know that max would be 0. So we're left with mg sine theta equals ff. And if we're dealing with the maximum force of static friction, then we can use this equation for ff, mu fn. Now, I am going to add in the F net, or the F net y equation up here, because that doesn't change between these two situations. That is still going to be Fn minus Fg cosine theta equals may. Since this object is not accelerating up off the ramp or down into it, the acceleration in the y direction is 0. So we see that Fn equals mg cosine of theta. I can bring that down here, and then I have mg sine theta equals mu mg cosine theta. I have an mg on both sides. They cancel out. I'm looking for mu, the minimum coefficient to hold this in place. I divide the cosine theta over to the other side, and I get mu equals tan theta. So the coefficient of friction has to be equal to the tangent of the angle that the ramp makes with the ground in order to hold this in place. And again, this is for if we're dealing just with sliding. However, a lot of times objects won't slide down a ramp. They would, I don't need that. Objects won't slide down a ramp, they will instead roll down a ramp. Okay, and why would they roll? They would roll because of the friction on them. Now, there can be friction without rolling. Let's say you had, I don't know, like let's say this was a rectangular prism, a box of some sort. That doesn't have to roll. But this sphere, since we're calling it a sphere rolling down, that would obviously roll if there was friction. So it rolls because of the friction. Otherwise, would slide. Now, if we're saying it's going to roll, that means we need to also include torque in our analysis. So I'm going to actually draw a similar free body diagram, or it's not going to be a free body diagram, it's going to be the force diagram for the entire object this time. And again, this is the rolling case. Here's our object. We're going to do our same axis, x, y, and because the object is going to roll and accelerate down this way, we're going to say that the clockwise direction is positive, I believe. Yes. Okay. Let's see here, and this is, again, our sphere. The forces acting on this sphere. We have the force of gravity acting straight down from the center, so that's Fg. We have a normal force acting up perpendicular to the ramp surface, like this, Fn. And we have a force of friction. Remember, when we're dealing with torques and we're drawing these, we're doing this analysis where the twisting or rotating or spinning of an object is important, we have to draw the forces exactly from where they act. The force of friction acts from the point of contact between the ball and the ramp. So that's in right here, and it is in that direction. The reason it is in that direction is because if the ball were to simply slide down the ramp this way, then that would mean that this point is traveling relative to the ramp surface, it's traveling to the right. So that means the force of friction would be back to the left. Only thing I have to do now is split Fg up into components. And that's going to be done the same way that the other one was done. Fg cosine theta and Fg sine theta. So our net force equations actually look exactly the same. I'll rewrite them. F net x equals, let's see, Fg sine theta minus Ff equals max, and F net y equals Fn minus Fg cosine theta equals may. Now, again, in the y direction, there's no acceleration, so that's 0. So Fn still equals mg cosine theta. What we want to do now is talk about the acceleration for any case, okay, if this is going to roll. If it's going to roll under the very strict conditions of rolling without slipping, then this could be kind of hard because it doesn't seem like we know how big the force of friction is or what the acceleration is. So it's kind of like we have one equation, two unknowns. We can't just substitute in and say that Fn is equal, or Ff equals mu Fn, because we don't know if that force of friction is, if it's the minimum force of friction, or the maximum force of static friction in this case. So unless we know that if we're talking about the maximum force of static friction, we can't say that. What we can do, however, is look at the torque, because that's how this object is going to get spinning and have a rotational acceleration. The net torque on the object would be equal to the torques from all the forces. Force of gravity doesn't exert a torque because it acts at the center of rotation. Here, let me just, don't know if this is Ff max. All right, so let's see. The net torque, actually, we're going to save that equation for a second. Only the force of friction causes a torque. The other two forces act either at the axis of rotation in the center of the sphere, or parallel to the line between the axis of rotation and point of application of the force. In other words, the other two forces on this, the force of gravity acts from the center of rotation, so that's not going to cause a torque. The normal force does not, but it is aligned in such a way that it is anti-parallel to the displacement vector from the center of rotation, or the axis of rotation, to where the force is applied, so that also does not produce a torque. The force of friction is the only force to produce a torque, and you can see that that torque would cause counterclockwise, or clockwise, rotation, so that's going to be positive given our reference frame. So I have tau net, equals the tau torque from the force of friction. And remember, the net torque is always equal to I alpha, the moment of inertia multiplied by alpha. And by the way, I should say that for this sphere, we're going to treat this sphere as having a radius of r, and I for a sphere is 2/5 mr squared. Okay, so talking about the amount of torque from the sphere, we have r for this force times the force of friction itself multiplied by sine theta f. You can tell that this is the radius and the force of friction acts perpendicular to that, so that's going to cross off and be 1. That equals 2/5 mr squared. And do remember that alpha is equal to linear acceleration, in this case in the x direction, over r. So we're going to change that right away. This is ax over r. Notice I have r squared and then r on the bottom here, so that's going to cancel out. The radius, or the distance that the force acts from the center of rotation, from the axis of rotation, is r. I'm just going to leave that there. Equals 2/5 mr ax. We now have an r on each side. We're going to cancel that out. And we see that the force of friction in causing this smooth rotation must be equal to 2/5 max. Interesting. What we're going to do with that now, and you can see that that's regardless of what the coefficient of friction is. We haven't done anything with mu right now, okay? All this says is that if this is rolling smoothly, this must be the size of the force of friction, which is kind of interesting. We're going to take this and we're going to plug it into our F net x equation. Nope, I'm not going to write that again. So we have mg sine theta minus, let's see, did I do this right? Minus 2/5 max equals ax. I just took this equation up here, I brought it down here, and I made a couple of substitutions. Instead of fg, I wrote mg, and instead of ff, I found what we saw for when we did the torque analysis. We want to get the acceleration. We want to know what the acceleration of this object is. So I'm going to add the term with the acceleration over to the other side. Actually, I'm going to cancel out all the mass terms first, m. I'm going to add the 2/5 ax to the other side, and I get g sine theta equals 7/5 ax. If I want to solve for the acceleration, I multiply both sides by 5/7, and I end up with this. 5/7 g sine theta. And if you look, you can tell that that's actually less than the acceleration for sliding when there is no friction, when there's no friction as it slides. If it rolls, the acceleration will be less than that. Less than for sliding with no friction. Okay? Which is interesting. So if there's less of an acceleration, the object won't move as fast. And that goes back to what I said before about an object sliding versus rolling. The sliding object will move faster, will have more translational kinetic energy. The other object will have more rotational kinetic energy and will not move as fast because some of that energy has to go into rotating the object. If, on the other hand, we are looking for the minimum mu to allow sliding, in other words, let's see, the maximum force before object stops, object held in place, then we come back to this equation right here. Wait a sec, do we come back to that one? Give me 1 second. Okay, yes, we come back to this equation right here, where we have Fg sine theta minus Ff equals max. So no matter what the force of friction is, if rolling is occurring, there is one acceleration for this object, which is kind of interesting. Let's see here. We're going to change this to mg sine theta. If we're looking for the maximum force of static friction, meaning the minimum mu allowed, then this is going to be mu Fn, and then this is going to be m times 5/7 g sine theta. The normal force, as we found before, is mg cosine theta, so I'm going to have mg sine theta minus mu mg cosine theta equals 5/7 mg sine theta. We have a lot to cancel out here. I have mg's in each term. Those are gone. I also have a sine theta and a 5/7 sine theta. If I subtract one full sine theta from 5/7 sine theta, what I'm going to be left with on one side is mu cosine theta equals negative 2/7 sine theta. I'm missing a term. Wait a second. Oh wait, no. Am I? Okay, no, I'm good. All right. I have negatives on both sides. Those cancel out. We just get positives. I divide both sides by cosine of theta. And I end up with mu equals 2/7 tan theta, which also compares interestingly to the minimum to hold it in place. To hold it in place, we need tan theta, okay? To allow for rolling, or to allow sliding, no, to allow rolling, we only need a coefficient of, we only need a coefficient of friction of 2/7 tan theta, okay? So ultimately what is happening here is that, and I kind of explained this before, since the acceleration is less, the object does not accelerate as fast, so it has a slower speed at the bottom. Rolling produces slower speeds than sliding does. And this agrees with what we found earlier with splitting the kinetic energy into translational and rotational. Okay? I'm going to do one more video in which we compare the moments of inertia and we see how moment of inertia can affect things like the energy and the speed of an object as it gets to the ground.